So what we have said is that when you have two functions, and they can be intersecting functions or they can not be intersecting functions, that doesn't matter. I'll kind of make this one kind of 6 of one and half a dozen of the other. If I said to you, what is the area between these two functions? From x equals a to x equals b, and we'll just call this one f of x and this one g of x. What I have taught you is that this area will be the integral from a to b of the difference between the two functions. Where you're subtracting in the order of upper minus lower. And you might have noticed that what I just drew here doesn't make any reference at all to the location of the axes. I've talked to you before about why the location of the the y-axis doesn't matter, and it has to do with the fact that you could always translate these two functions to the left or to the right, however far you need to translate them in order to put them into a positive realm for x. And that, of course, changes the functions. But based on the properties of translations in terms of shifting left and right, you're going to end up getting the same result. It's not going to matter. And, you can take this as far as you want, just logically speaking. This area will be what this area is, so why should it change if I move the two functions a million units to the right or a million units to the left? It's the same area. Similarly, this one is a little bit easier to explain. If it turns out that the x-axis, happens to be, I don't know, here, all you have to do to ensure that they are both above the x-axis is add some amount, whatever amount you see fit, to each function to push those functions above the x-axis. Now, I don't have room to do that, but I hope you see that if I do shift these up 30 units, the x-axis will now be below the functions. And it's very easy to see that when I put in this along with brackets around the second function, that the result is the same. Whether you get rid of that plus 30 minus 30 before you anti-differentiate or after you anti-differentiate doesn't matter. So in the end, just to go back a couple of steps, what is important is that you understand that's how you find the area. And sometimes you're given the lower and the upper boundaries, and by lower and upper I'm talking about minimum x and maximum x. Well, sometimes you have to find those boundaries because there are points of intersection. So you might have some legwork to do, algebraically speaking, in order to find them. So I kind of sifted these out into 3 piles: basic, intermediate, and challenge. Does anybody have any questions you would like me to go over from any of these? Yeah. S? Okay. So there's going to be a lot of prep work here because we have to look at what these functions look like. Sine of x and cos of 2x from pi over 6 to 5 pi over 6. So luckily these are both positive values of x. And the only reason why I'm saying luckily is I'm better, and I'm sure you are, with sketching the graphs in a positive direction than a negative. So I'm going to do a rough sketch here using my knowledge of trigonometric functions from Math 30. by only going from 0 to pi. I know that the period of sine of x is 2 pi. And if I can just make a little tiny sketch up here to refer to, for sine of x, that's what y equals sine of x looks like roughly. Now what that means is y equals sine of x from 0 to pi will we should also know that it goes one above and one below, right? And I'm just doing this so that I can make sure my graph looks fairly decent. So since this is pi, and I'm only going to pi here, Craig, because this is between pi over 6 and 5 pi over 6. Since that goes up to pi, and this graph in the top right corner goes up to 2 pi, what this graph will look like is it will go up from the origin, it will max halfway in between, and because I can, I'm going to put a ruler down and what was that, 16.6, that's 8.3. I just want to do a fairly decent graph here. 8.3 would be about close enough. So what this graph will look like in the region we're interested in is that. Okay, so that's y equals sine of x. Now, what does cos of 2x look like? Cos of x, what I'm putting up here is for my own benefit as well as yours. Like if I were working on this on paper, I would be making these sketches rather than using my graphing calculator. Cos of x starts at the top, goes down, and ends up there. That's cos of x. But cos of 2x from Math 30 has a parameter of b, and the period is 2 pi over b, which means the period of this cosine function is 2 pi over 2, which means the period is pi. So the sine function from 0 to pi goes through half a period, but the cosine will go through a full period. And cosine starts at the top and ends back at the top. I realize now that I moved that pi over, so it's not going to be perfectly symmetrical, but that's okay. And that means it minimizes here, and it will cross the axis halfway in between. I'll just eyeball this. That's pretty good. This one will be off, of course, yeah. Good enough. And again, I'm just playing around with the tools I have available so I can do a rough sketch. So cosine of 2x looks like that. Good? I'm guessing, even though I haven't done the algebra, and I'm hoping that this is pi over 6 and that this is 5 pi over 6. It sure would be nice, and I think if it wasn't, it would not be an intermediate type of problem. So now what you do have to do is confirm that algebraically. You know, we have time today. The lesson is relatively short today. And I think it's important you understand we are not doing stuff in this class with a graphing calculator all the time, right? So if I want to find the points of intersection of y equals sine of x and y equals cos of 2x, then I have to solve that equation. And that would mean the y's prudent move would be to write 1 minus 2 sine squared of x for cos of 2x so that I have a quadratic equation in one type of trig function. Zeroing this, the trig function that I'm talking about, the type is sine of x, obviously. I get 2 sine squared of x plus sine of x minus 1 equals 0. It seems to me I just said this maybe one time last week or the week before. This is like a quadratic trigonometric equation that you see again and again and again, this 2, 1, 1 thing. And the sign may change on the middle. It may be positive or negative. Did I rearrange that right? 2 plus plus minus, yeah. So 2 sine x, and it will be a 1. Sine x, and it will be a 1. What do I want? A positive sign in the middle. I think that does it. To get positive 1 sine of x for my outer and inner combined. Which means, there you go. Sine of x is 1/2, which happens at pi over 6 and 5 pi over 6. These will also intersect when sine of x is negative 1. Oh, well, that's not going to happen until over here at 3 pi over 2. Is that right? Yeah, 3 pi over 2. So I didn't really finish this clearly, but this is x equals pi over 6 and x equals 5 pi over 6. So that means our integral will be from pi over 6 to 5 pi over 6. Because, everybody, combining my algebra with what I know the graphs must look like, I've confirmed these are the intersection points, and that means I've confirmed that this is the area I care about, and that means that it can be done with one integral where one of the functions lies entirely above the other function in the interval, and it is the sine function that lies above the cosine function. And although if we were trying to algebraically work with these two functions, we would use an identity to get sines with sines, I don't think we want to do that. You could certainly put this in for cos of 2x, but anti-differentiating 2 sine squared of x is an interesting prospect. And I'll come back to that later if I feel the need to, because I think it's an important thing to think about. So, we are going to have to then take negative cosine of x, which is the antiderivative of sine of x. Hope I'm not alone on that. Minus 1/2 sine of 2x. 1/2 sine of 2x is the antiderivative of cos of 2x. Yes. And evaluate this from pi over 6 to 5 pi over 6. And I certainly don't mind doing that, but is that your concern? Okay, so let's finish the problem off. It does tend to pile up. There's a lot going on here. So I need to take, now, I would be really tempted to factor that negative 1 out, and that has a lot to do with what we're going to talk about today, but I'll leave it in. We're going to have negative cosine of 5 pi over 6 minus 1/2 of sine of 2 times 5 pi over 6. And if it were just me doing this and I weren't worried about students and questions and learning, I would have written 5 pi over 3 there. And then I need to take that and subtract the same thing when I put pi over 6 in. And same kind of thing If I were doing it on my own, I probably would have just written 1/2 sine of pi over 3. So I want to double check. There's my integral, my antiderivative. I'm just going to actually differentiate this just one final time to make sure I've anti-differentiated properly. Derivative of negative cos is positive sine. The derivative of negative 1/2 sine of 2x is negative cos of 2x times 1/2 times the 2. It's okay. So I'm focusing my attention now on two positions unit circly speaking. I'm looking at 5 pi over 6. I'm actually looking at a number of places. I'm looking at pi over 6. I'm looking at pi over 3. And I'm looking at 5 pi over 3. Well, I'm highlighting an angle here. I haven't highlighted an angle up top. That's just a position, but we know that it corresponds to that angle. That may be picky, but I think that's important. This is, no. 5 pi over 3. We're not interested in this one. We are not interested in that. This is 5 pi over 3, which is 1, 2, 3, 4. That, am I right? 5 pi over 6 times 2 is 5 pi over 3. 1, 2, 3, 4, 5. That's right. We are interested in the pi over 6 position, and we are interested in 2 times pi over 6, which is pi over 3, which is here. So, remember, we've got 4 different angles here, I suppose. Cosine is an x-coordinate, sine is a y-coordinate. There's a lot to be organized about in your head here. So negative cos of 5 pi over 6, the cosine of the yellow point, or rotation angle that takes us there, is the x-coordinate, which is negative root 3 over 2, but it's negative cos, so this is root 3 over 2. Minus 1/2, the sine of 5 pi over 3, which is the rotation to take us to the yellow point. The sine is negative root 3 over 2. I mean, this is going to change to positive, but I'll leave that for the next step. We don't need this set of brackets, but I like it for completeness sake. We do need this next set of brackets. Cosine of pi over 6, cosine is root 3 over 2. Cosine of pi over 6 is root 3 over 2. And it's negative. And then we have minus 1/2 times sine of pi over 3. Well, everything's going to double up here, I think. The pink point, which is the rotation angle pi over 3 to take us to that point, has a sine value, a y-coordinate of root 3 over 2. And I'm just going to double check everything. Negative cos of 5 pi over 6. 5 pi over 6 is negative root 3 over 2. Negative root 3 over 2. Minus 1/2 sine 5 pi over 3. 1, 2, 3, 4, 5. That's negative root 3 over 2. Minus cos of pi over 6 is root 3 over 2, and it's times a negative. Minus 1/2 sine of pi over 3 is root 3 over 2. It all looks good. I said I think things are going to double up because what we end up with here is root 3 over 2 plus root 3 over 4. And what we end up with here, you can do it in a couple of ways. You can combine these and then change the sign, or you can multiply that negative through, which is probably what I would do. You end up with another root 3 over 2 plus root 3 over 4, which the brackets at this point are totally not necessary. So what do we have? We have, well, I was gonna put the root 3 over 2's together and say root 3, but we're going to need to add them as fractions. So I would say this is 2 root 3 over 4 plus root 3 over 4 plus 2 root 3 over 4 plus root 3 over 4 all I'm doing here, everyone, is I'm taking these and putting them over a denominator of 4. So then I have 2 plus 1 plus 2 plus 1 is 6. Root 3 over 4